Welcome everybody. I'm Professor Renato Spigler. I originally graduated in engineering, but I've been for all my life an applied mathematician. That means that I use mathematics to apply it to applications, to apply it to engineering and to sciences, typically physics, using computation and using theoretical devices. I was interested mostly in research, but I've been teaching quite a bit applied mathematics and also analysis. And I'm going to introduce you to my course. The title is Advanced Mathematical Methods. This course concerns some topics typically pertaining to mathematical analysis. And the course, more precisely, consists of three main parts. The first is entitled Holomorphic Functions. These are also called analytic functions, but there are some differences in this terminology that I'm going to describe in the course. Holomorphic functions are, generally speaking, loosely speaking, functions of complex variables. Complex variable, and the result is also complex. So the change with respect to the real variables that you have been studied in calculus courses is outstanding, is very important. There are many differences that are very relevant. And many results come from this theory. It's a fascinating theory, it's beautiful, and it has some fallouts. For instance, you can compute integrals that are not easily computable with the real variable techniques. This is one thing. Another part is the Fourier series and integrals, and in particular Fourier transform. Fourier series are also another fascinating subject, because they go back to the mathematician Fourier, who lived at the time of Napoleon, and he actually derived this series as a tool to solve the so-called heat equation. The heat equation is an equation that describes transfer phenomena in solids, typically of heat and temperature. So this equation was something difficult to handle, and Fourier developed this tool just for that. But the consequences were far-reaching. This happens always in the history of mathematics and of science, that something is developed for some purpose, but it turns out to be useful in many other fields. And periodic functions are ubiquitous in life, so Fourier series can be used to describe them. Could be electrocardiograms, or seasons, or speech and music, for instance. So they are all related to Fourier series. The third subject is called the Laplace transform. Laplace was another famous mathematician, a French mathematician who gave a big contribution, and the tool that he developed turned out to be useful for engineers, electrical engineers, to solve circuit equations much later in time, because Laplace lived at the time of the French Revolutions, and there was not such a thing like circuitry at the time. So this is also another interesting fact that occurs in history of science. There are some requirements for this course. The point is that it's strongly advisable that people know some mathematics preliminary to some mathematics that comes after it, naturally. You cannot study different equations even in the junior high school, algebraic simple equation, if you don't know an element about numbers, naive element, but something about operation, addition and products, and so on. So for the same token, you cannot study Laplace transform or Fourier transform that are integral transforms, so they involve integrals, integration, without knowing limits, continuity, derivatives, integrals, so the tools basic in calculus courses. So it's very advisable to be familiar as much as is possible with the calculus subject, and more precisely, the reader should be familiar with the main element of calculus in one and in several variables, complex numbers, and the basics of differential equations, if possible. There are other things like a series that would be nice to know. In some courses in calculus they are taught, maybe in some other they are not. Anyway, I will make an effort to keep the course self-contained, reviewing some elements on complex numbers and differential equations and series when needed, so that you may be relatively released from the need to be too much familiar previously. And in closing, I would say that this course traditionally comes after some calculus course. It was introduced in many universities long ago to support the extra needs of mathematics that engineers have. So it's something that is useful. Of course, it's useful in the sense of mathematics. If you enjoy this logic, the rationality intrinsic to mathematics, then you may enjoy also this subject. And it is useful because this course may provide the key to understand a lot of things pertaining to courses of engineering and in applications of science and engineering. I hope that you will join me to attend the full course.